All right, so we continue with the general problem of rolling without slipping, and we do a different example today, a bit more complicated than the one that we did in the last lesson, right? So what we have today is a cylinder rolling down an inclined plane instead of a sphere rolling on a flat surface. Okay? So we have a cylinder of radius r, and it's rolling down a plane which makes an angle theta with the horizontal from height h, right? So let's say we want to find out what is the acceleration of the center of mass of this cylinder in this direction. What is it? Any guesses?
So इसका area?
Area of what?
नहीं, आप इसका area पूछ रहे हैं या acceleration पूछ रहे हैं?
Acceleration.
So वो तो mg sin theta नहीं होगी?
mg तो नहीं होगा, g sin theta होगा ना, ठीक है?
हाँ, वो g sin theta, sorry.
Well, this is not a bad guess because that's what we know, that what happens when we have a block sliding down, because we've been doing those examples, right? That a is equal to ag sin theta. So let's.
This is a sphere rolling down.
This is a cylinder rolling down.
Okay, thank you.
Okay, so let's say that if this is the correct answer, let's box it for a minute, and we would check that if this is correct or not. Okay. Now let's start with the usual thing that we do. Look at all the forces that are acting on this object. What are all the forces acting? Forces, please.
Weight and normal force.
Weight, mg, and normal force, and we have friction as well. So friction कहाँ पे होगी?
तो पीछे की तरफ होगी ना, up the hill.
Upward. Okay, very good. And now you do not forget, we are no more dealing with a point particle. So it really matters which point of the object the force is acting on. Okay, whether the force is acting on along a line that passes through its center, or it is acting along a line which is just tangentially touching it. This is very important, right? So 3 forces, and that is more or less it, no? But before I start solving this problem, now look at this. If there was no friction in this situation, what would happen? If there was no friction and initially the cylinder is not rolling, what would happen then? It would
Sir,
just
if friction नहीं है तो वो initially move कर रहा होगा ना, कि what is the force that keeps it from not rolling down अगर friction है ही नहीं?
No, I mean, let's say that we do not roll it, so we just place it. It's not initially rolling. Omega naught is 0. We place the cylinder here. There is no friction, and we release it. What happens then?
I think it'll just slide down. It won't roll.
It would just slip down. It would not roll. Okay, and then all the equations that you have a block sliding down, you can just treat it like that. Very simple. Okay, for this object to roll, we must have a non-zero friction case. Okay, so let's say that we have a friction. So this is the case that we are considering, that force of friction is not 0. Okay, so what is the component, the force acting along this direction? What is that? Hmm? The component of weight acting along
So
this
mg
direction.
cos theta.
mg sin theta नहीं होगा.
नहीं sir,
mg
cos
sin
theta
theta.
होगा.
कोसाइन होगा या
mg
sin?
sin.
जी सर, ये साइन होगा, सॉरी.
क्यों साइन होगा?
क्योंकि सर दी एंगल ऑन, मैं आपको बताती हूँ, ये बेसिकली, हाँ सर, ये जो ये बेसिकली एंगल है ना बिटवीन द परपेंडिकुलर लाइन फ्रॉम द प्लेन, और सर ये नहीं थीटा होगा आई थिंक.
इधर वाला एंगल थीटा होगा. है
हाँ एग्जैक्टली.
ठीक है. गुड. All right. So the force acting. So let's say first we write the equation along this direction. Okay. So we have mg sin theta minus f, the force of friction in the opposite direction, would be equal to ma. All right. Now what is the force of friction here?
Mu mg cos theta.
Okay, but let's first consider this. This would be mu n. Okay. And then if you take this to be mu n and then write it as mu mg cosine theta, okay, then you can plug the friction here and write the acceleration. A equals g sine theta minus mu g cosine theta, right? ये आ जाएगा acceleration का expression. ठीक है? Is that all right?
Yes sir, समझ आ गया.
Okay, but then then we have to introduce another assumption. So we are assuming that the moment we release this cylinder, it immediately starts rolling without sliding. There is no slipping. Okay, there is no sliding and pure rolling, only rolling. Okay, if that is the case, that if it is not sliding, then the kinetic friction would be zero, no? We cannot apply the kinetic friction because it's not slipping. The point of the cylinder which is touching the surface, the inclined plane, is not moving relative to the surface because it's just rolling. Any point that comes into contact with the surface leaves without, and so let's say that a point on the cylinder comes into contact with a point on the slide, on the inclined, these 2 points. So the point on the cylinder, it comes into contact with the surface, whatever point it comes into contact with the surface, it leaves it like that. So there is no slipping. There is no relative motion between the surface of the cylinder and this surface. So there would be no kinetic friction. There would be no kinetic friction. So what about, so this equation we cannot use. Fk mu kn. This we cannot use.
एक्सक्यूज मी सर, अभी स्टार्ट में आपने बोला था कि अगर फ्रिक्शन जीरो हो जाएगी तो फिर आपने बोला था कि अगर फ्रिक्शन जीरो होगी इट वोंट रोटेट, इट वुड जस्ट स्लिप डाउन, और अब आप कह रहे हैं कि अगर फ्रिक्शन जीरो होगी तो वो स्लिप नहीं करेगा, सिर्फ रोटेट करेगा. कैन यू प्लीज क्लियर दिस?
Yes, but I just said kinetic friction zero है. सिर्फ ये भी नहीं कहा कि
So
zero
what do
है.
you mean by
ये क्या है कि
kinetic friction?
जी सर, काइनेटिक और नॉर्मल फ्रिक्शन में क्या फर्क होगा?
जो kinetic friction होती है ना, that's exactly Fk is equal to mu Kn. ठीक है? और जो static friction होती है, that is, its maximum value can be mu n. ठीक है. If you feel uncomfortable, you can just erase this subscript. Now you see, although the mu's are different in two cases, but we did this in the very beginning when we introduced the force of friction. When you're trying to move an object on a surface, okay, and there is no motion still, so there is a force opposing the motion. That is static friction. Okay, and as you increase the force, this static friction keeps increasing, and the maximum value that it can get is mu times the coefficient of friction times the normal force, the force that I'm
Right.
exerting. All right. Once you have hit the maximum, and
Right.
then your force is the force that I'm applying becomes larger than mu n. All right. Then it would start moving, but friction hasn't gone away. The friction is still opposing the motion, but the friction that now is opposing the motion now is different. Okay. It's kinetic friction, and kinetic friction has this exact relationship. There is no maximum minimum. Okay, so it's always equal to mu times n. That's
तो
kinetic
सर जो
friction.
ऊपर हम फ्रिक्शन कंसिडर कर रहे हैं वो भी हम मोशन की वजह से फ्रिक्शन नहीं कंसिडर कर रहे और उसकी भी वैल्यू म्यू एन यही भी आपने ऊपर ही लिखा हुआ है F equals to म्यू एन. That's also the friction due to motion, right? और kinetic friction भी यही होती है.
हाँ, बिल्कुल सही है. ठीक है. But now we are saying that we cannot apply this kinetic friction because we are assuming pure rolling. इसमें तो rolling भी हो सकती है, sliding भी हो सकती है. ठीक है. We are assuming that there is no sliding. When there is no relative motion between the surfaces, then kinetic friction वाली equation you can't use it.
Right.
Okay, there is no relative motion. However, there is a force that is trying to slide this cylinder downwards. You see, there is a force mg sine theta, and there is a force of friction that is opposing that slide. All right.
जी.
And that is static friction. That relation is like this: Fs less than equal to can be anything smaller than mu n. Okay. But we have no way of knowing what this friction is. All we know is that its maximum value is mu n, but it can be anything. Okay, I'm saying friction is there, but we don't know its expression, so we cannot use this formula now that we used before in this case. Once we
Sir.
introduce pure rolling.
Okay.
All right. So we would just use some other way to find out what friction is. Okay. And then find out the acceleration for the case when you have pure rolling without sliding. Okay. So it is the same equation. The only thing that we won't do is we won't plug in F equals mu n in this equation. I'll just rewrite it.
तो सर ये जो एक आखिरी चीज़ है कि ये जो इक्वेशन आपने ऊपर बनाई है ये तब के लिए when there is rolling as well as मतलब transitional movement भी हो रही है कि वो नीचे भी जा रहा है और साथ रोटेट भी कर रहा है.
Yes,
है ना?
yes, yes.
Thank you.
Yes, when both sliding and rolling you have, that's the only place where you can use F is equal to mu n, when you have both. If you have pure rolling, then you cannot use this equation, and would just take this and find another way to find the acceleration. Mg sine theta minus F equals ma. All right, but this is only this only deals with translational motion along the surface of the incline, right? Now we have to, and then this only describes the center of mass. Now let's talk about the rotational part of the motion. So we go back to the picture. What is torque due to the weight, mg?
0, sir.
0. Why?
Sir, it is passing through the center of mass.
Yes, exactly. So what is torque around center of mass due to normal force?
Also 0.
Also 0. So what is torque due to the force of friction?
Friction into R.
Friction into R. Very good. So the torque is simply FR. They make 90-degree angle, right? And we also know that torque is nothing but I alpha, where I is around the center of mass. So from here, and we also know that I for a cylinder is half mr squared, right? So from here we can calculate, we can just equate the two torques, Fr I alpha. Now introduce the value of I, and one more thing. So what is the condition? We did this, we did drive this condition, rolling without slipping. What is that? What is the condition? What is the relationship between rotational and translational motion once we are assuming rolling without slipping?
The velocity of center of mass is equals to tangential velocity.
More or less. So the velocity of the center of mass is equal to, yes, that's exactly the answer, is equal to the tangential velocity, which is r omega, right? Now take a time derivative on both sides and you get the acceleration of center of mass equals r alpha.
Okay, sir.
Okay. Now you have to be careful. Probably there is another relationship between tangential acceleration and alpha, right? And I think it looks the same, doesn't it? But this relationship comes from the condition rolling without slipping. And this is the center of mass acceleration related to the rotational acceleration. So these two relationships are different. These two equations are only true if we have rolling without slipping. Okay. Do not confuse with this other relationship where you have V is equal to R omega, because that V is tangential velocity. Okay. Here we have equated the center of mass velocity with the tangential velocity. This is tangential velocity, and this is tangential acceleration. Sorry, rotational acceleration. And this itself is a tangential acceleration. Now, if you introduce the value of alpha from here and I and alpha from here into the equation that we have here and simplify it for F, what do we get? Can you do it for me, please? What do we get? The expression for F after introducing I and alpha from there.
Sir, half MA?
Half MA, very good. F is equal to half MA. Okay. So we have found the expression for friction, not using the traditional definition F is equal to mu K, because it's no more valid. Okay. And now we go back finding the acceleration. Now we go back here. We introduce the value of F into this equation, and we find the acceleration for the case of rolling without slipping. This is rolling with slipping. So what does, substitute F in here and solve it for A, please.
Sir, 2/3 G sine theta.
2/3 G sine theta, very good. All right. Now, this is the acceleration of the center of mass for the case of rolling without slipping. And what is the acceleration? Somebody answered it at the very beginning and we wrote it up there. So do we get the same answer? A is equal to G sine theta? No. You will get A is equal to G sine theta when you have no friction and you're only sliding. Okay. Then you will get A is equal to G sine theta. When you have friction and you're sliding, then you will get G sine theta minus mu G cosine theta. And when you have pure rolling, okay, pure rolling, then A is 2 by 3 g sine theta. You see, this is different from A is equal to g sine theta for the blocks and point particles that we have been calculating. All right. So we said that the friction has to be to induce rolling. If the friction has to be finite, non-zero. But you see, if the friction is not enough, friction also has to be larger than a minimum value of a particular value of friction. So that if the friction is smaller than this, then it may not introduce rolling. Okay, to get pure rolling without sliding, there is a condition on the friction, that the friction must be larger than a particular value of friction to ensure pure rolling. Okay, because if you have a smooth surface, then you won't have rolling. Let's find out that. Okay, find that out. So F minimum is nothing but half MA. Okay, and now we know the value of A. What is the value of A? We just calculated
2 by 3 g sine
by
theta.
3 g sine theta.
2 by 3 g sine theta. Right. So the F minimum turns out to be 1 by 3 mg sine theta. And what is the maximum friction that you can get from a surface? What is the maximum friction? Mu n, right? And that is nothing but mu mg cosine theta. Now we have this condition that this minimum friction can be equal to the maximum friction that the surface can provide, or less than that. Of course, it's a constraint. The minimum friction at which you would beyond any value larger than this would give us pure rolling. Any value smaller than this would not give us pure rolling. Okay, but this itself cannot be larger than the maximum friction that that surface has. Okay, so that means F max and mu mg cosine theta, and on this side we have 1 by 3 mg sine theta. Mass cancels, g cancels. Okay, and if you simplify this further, you get a condition tangent theta less than or equal to 3 mu. What this means is that if the slope is too steep, if the slope is too steep, we won't get pure rolling. Or if the friction is too small, if the surface is too smooth, again, we won't get pure rolling. Okay, so we have to strike a balance between these two quantities. If you have low friction, you may still get pure rolling with a very small angle. Okay, and if you have large friction, then you can afford a large angle, but there is a limit on that. Okay, however large this mu is, okay, there is a limit on that. So once you set mu, then you can decide how big an angle you can have, how steep the plane can be for you to ensure that you still get pure rolling and no sliding. Once you go larger than that angle, then you would, even despite having a very large friction, you would still be both sliding and rolling probably. Is this clear?
So yeah, please tan theta less than or equals to 3 mu के बारे में आपने जो बताया है कि how the angle could vary with the value of mu, या please repeat कर सकते हैं?
So what I'm saying is, let's try to make a different picture. Let's say that this surface has a friction, okay, and its coefficient of friction is mu. So what is the maximum friction that you can get? Mu n,
Right.
right? So in this direction. And what is the downward force?
mg cos theta. Oh, sorry.
mg sine theta, right?
Right.
Now for pure rolling, okay, for pure rolling, this point here should have zero acceleration with respect to this surface, should not move at all, point of contact. That means
Well,
these two forces should be equal. All right. Now what I'm saying is that whatever the value of friction you have, if you make the angle bigger, okay, you're making this force bigger by making the angle bigger, but this force doesn't depend on angle. Mu and friction doesn't depend on angle. It is going to be the same. And if anything, it's going to be less because the normal force decreases if you increase the angle. So the friction is decreasing, and the weight along this, the force along this surface is increasing. So
जी sir, friction decrease करेगी ना, क्योंकि if we bring it to a 90 degree तो फिर तो friction होगी ही नहीं ना.
बिल्कुल. So friction is decreasing if you increase the angle, and this force is increasing. What that means is at some point it would sliding down, it would start sliding down.
Right.
All right.
Hmm.
And if you decrease the angle, okay,
जी.
if it is sliding down and you keep decreasing the angle, at some point there would be a particular angle at which, for a given friction, you would be able to roll pure, you would be able to have pure rolling. So what I'm saying is, if this friction is large, then you can afford larger angles and still have pure rolling. And if the friction is small, then you can only have very, very small angles where you will get pure rolling. If you increase the angle for small friction, it would keep sliding. You can't stop it. That's what that relationship is saying.
Sorry. Okay. Thank you, sir.
So the other situation, what if that you don't have this relationship? When this relationship doesn't hold, for example, you have a larger angle, then the friction can allow for pure rolling. What happens then? All you have to do is then solve these two equations to get all the quantities. Once that relationship breaks, then you just have IFR equal to I alpha. And the other equation is, for the translational motion, is mg sine theta. And now you can use the exact expression for the force, for the friction, mu mg, because you actually have sliding. So you can use the maximum value of friction in the equation equals to ma. ठीक है? Once you don't have this equation or this inequality holding, tangent theta less than equal to mu. That is the two equations that you must be solving. Now this was all done in the center of mass frame of reference, okay? All this problem. So I encourage you to do it in a lab frame of reference, and this is given in your notes. You can please try to do it on your own. Now let's do the
सर नोट्स अभी तक अपलोड नहीं हुए वैसे.
they are being corrected, so you will get them in a day or so, in a day or two. I'll ask Dr. Adam.
जी ठीक, थैंक यू सर.
Now we're going to do this exact same problem again. Okay. And this time, instead of using the Newton's second law, we're going to use the energy method. Okay. We learned energy method from translational motion, and for rotational motion, we're going to use it now. Okay. So, and how do we begin? So the question is, as the cylinder rolls down, it gathers speed, right? Goes faster and faster, and it is coming down from H. So how much, sorry, it shouldn't be H bar. So how much potential energy it loses when it goes from the top of the wedge to the slide to the bottom? The change in potential energy?
mg.
mgh. Okay. Now, if you see this, it is not just slide. It's not just doing linear motion. It's also rolling, right? So the potential energy would not go just into the translational kinetic energy. It would also go into, look, potential energy that is usually when, if this was a block or it's a point particle, all the potential energy would go into its kinetic energy, linear kinetic energy. Okay. And now we have two types of motion of this object. One is its center of mass is moving in a straight line, and the other is the object is rolling around its own axis. So it has two types of kinetic energy. So this potential energy from the word go, we know would convert into two components, or would convert into two types of kinetic energy: the rotational kinetic energy plus the translational kinetic energy, okay, of the center of mass. And this would be the rotational kinetic energy in the center of mass frame. Okay, but let's do that more concretely. Okay? So let's say that this is the cylinder, and this is its center of mass from an external coordinate system, a stationary coordinate system. R is the position vector of the center of mass, and then we consider a small point here, a small mass here, whose coordinate is R from this frame of reference and R prime from this frame of reference. All right. So what is the kinetic energy of this point if this object is rolling and translating? So the whole object, the center of mass, is translating. The kinetic energy of this point is simply half mi vi squared, right? From this point of, and here we disregard the rotational motion because we are not distinguishing. All we are just caring about is whatever the velocity this object has, which we don't know yet, times half times the square of that velocity times half of the mass gives us the kinetic energy of that object. That's total kinetic energy. That's the total kinetic energy of this little mass here. And if we add all those masses, we sum all those energies, that would be the total kinetic energy. K or K, doesn't matter, whichever way you prefer to write. Right. Now let's write.
तो ये रोटेशनल के लिए या ट्रांसलेशनल के लिए ये जो
दोनों
आपने
इसमें
किया?
दोनों शामिल हैं, both.
सही,
Okay.
okay.
This is general. We just take a small piece of the object and we don't worry how it is moving. All we need to know is its velocity. And if we know its velocity, then we can just from a stationary frame, an inertial frame. Okay. So we just get the energy of that point, total energy, and then if we sum over all such masses, then we get the total energy of the whole object. This includes both rotational and translational. Now look at these vectors, and we have used this relationship so many times before that R can be written as Ri, can be written as Ri prime plus R. All right. Now let's take a time derivative of this. So what do we get? Vi equals Vi prime plus V. Now this is the velocity of the center of mass as measured by an inertial frame, a stationary inertial frame. This is the velocity of a given point, a one point on that object as measured from this origin here. Let's call it O, from this origin outside the object. Okay. And this is the velocity of a point on the object, same point on the object as measured from the center of mass. Okay. So this equation. Now let's plug this equation back in here and expand the square. So if you expand it, you will get, this is nothing but just this, what is inside square is just the dot product of these two vectors.
Sir, isn't it Vi prime inside the square?
Yes, yes, it's Vi prime. Thank you. Yes, Vi prime, this vector, dot product, this vector. Okay, this is what the square is. Okay, so we multiply, we take dot product of Vi prime with Vi prime. So what do we get? Vi square, right? Then we get another term, V dot V, that would be just V squared. And then we would get Vi dot V and V dot Vi. And since we know that dot product is commutative, that would be just 2Vi dot V. Okay. So the first term would be half MVI squared, and this is MVI prime squared. Okay. The second term would be sum MI V squared, the center of mass velocity squared. And the third term, there would be a half here. And the third term without the half, because there is a 2 coming from there, would be MI VI prime dot V. That's the third term. All right. So what is this now? By definition.
So ये sum of momentum हो जाएगा ना? I think.
Yes, that's also true. But isn't it, if you divide it by mass, isn't it the velocity of the center of mass in the center of mass frame?
Yes.
Yes. So this is the velocity of the center of mass because of this sum in the center of mass frame. Okay.
So it's 0?
So it's 0. So we're only left with 2 terms. I'll write them in the next board. And from here, even before we move, now what is this? What is this?
So kinetic energy of center of mass.
Yes, kinetic energy of the center of mass. And if you just simplify this sum, this is total mass of the object. Right? So this is the kinetic energy of the center of mass. Okay, and this is, we are exactly getting what we started with, right? What we said we would get: a kinetic energy part of the center of mass and a kinetic energy part associated with the rotation of the object. And this, you see, this velocity is of the object in the center of mass frame. So this is rotation. This energy is due to rotation, but it still doesn't look like that it's a rotational energy. We would rewrite it, okay? But this is clear, right? So what we have now is this: the total kinetic energy equals half mi vi prime n squared plus half mv. The sum of all masses is the total mass. Okay. Now this is clear. This is the center of mass, kinetic energy of the center of mass due to translational motion. Now let's say that this object is moving, is executing a fixed axis rotation. So fixed axis rotation means every point on the surface on this object is moving with the same angular velocity. Let's call that velocity omega. All right. So if that velocity is omega, then we can write 1/2 mi. And what is vi? Ri squared omega squared, no? Plus half mv squared. Now what is this? And everything else other than omega square, what is this?
So this is the position vector of the center of mass.
Yes, but it's
Moment of
multiplied by
inertia.
half moment of inertia. That's the definition of the moment of inertia. So moment of inertia around the center of mass, half omega square plus half mv square. And there it is. The total kinetic energy, that the object is gaining is the sum of the rotational kinetic energy plus the linear motion of the center of mass. This is all very good, but we haven't found anything useful. So let's say that now we have the change in kinetic energy. That is the gain in change in change in kinetic energy, which started with 0 and its final value is this. And we also have the change in potential energy, which is mgh. Okay, let's use these two energies, the potential energy or the change in potential energy and the kinetic energy, and assume that it's a conserved system. So no energy is being lost or obtained from internal forces or internal interactions. Okay, so if the energy is conserved, we can use these two equations to find out velocity. Okay, this velocity v. How do we do that? We just equate these two things. We say loss in the kinetic energy is equal to the gain in total kinetic energy, half IC omega square plus half mv squared, right? And now here you have to make two substitutions. One is, what is the moment of inertia of a cylinder? That is half mr squared. And there is another condition that v is equal to r omega, v, the center of mass v, okay, which is this v here. Okay, please make these two substitutions here. with value of omega and I in here and solve it for V. Please go ahead. Quickly, please. Is it difficult to solve it? All you have to do is plug in the value of omega in terms of V and R and I just simply and just then simplify and solve it for V.
The square root 4/3 GH आ रहा है.
Very good. So the V is square root 4/3 GH. Very good. But let's make sense of what this means, okay? Let's say that if you had a block sliding down, can you find out the velocity if you had a block sliding down without friction or with friction, doesn't really matter. Using the conservation of kinetic energy, if you had a block sliding down the same plane, what would be its final velocity? Can someone solve it? How would we solve it? Any ideas?
The square root 2GH हो जाएगी.
Bilkul, because what is the last in energy would be the same potential energy. The only difference in the kinetic energy would be that we won't have any rotations, only half mv square. Equate half mv square equal to mgh and then solve the velocity. क्या आएगा velocity का answer?
Sir, this is for if there's no rolling.
Yes, any object sliding, no rolling at all.
सर वो
No.
मैंने आपसे पूछा था कि आपने ये जो वी ओमेगा स्क्वायर को हमने पहले सब्स्टिट्यूट करना है ना वी स्क्वायर ओवर आर स्क्वायर से. और जो वी स्क्वायर है उसको हमने आर ओमेगा से तो नहीं ना करना सब्स्टिट्यूट.
नहीं, फिर v के लिए सॉल्व कैसे करेंगे?
हाँ एग्जैक्टली. तो सर जब मैंने इसको सॉल्व किया तो मेरा आंसर ये नहीं आ रहा 4/3 GH. मेरा कुछ और आ रहा है.
There is a probably just check your process. This is correct. I have three people's answer now.
4/3 ही है.
Yes. So this is the velocity of the center of mass once we have rolling. If we have no rolling, then pure sliding, no rolling at all, then the velocity would be 2gh. Which is larger?
2GH.
2gh. Does it make sense?
Yes sir, वो उसकी थोड़ी सी kinetic energy rotational में convert हो गई है.
Yes, because the total potential energy that has gone into the motion, some of it has in this case gone into rotation, and then the remaining has gone into linear motion. That is why the velocity associated with the center of mass of a rolling object is smaller than the velocity of an object which is not rolling. ठीक है? Okay, how about finding the acceleration from here, from using the energy method? So we have the total kinetic energy, which is half mv squared plus half I omega squared. Okay. Now again, if you substitute I here as you did previously and omega, both of them, and then simplify this. So again, substitute I equals half mr squared and omega equals V over R, and simplify this, please.
क्या करने सर?
You have to substitute the value of I and omega as you did in the previous case, and then simplify it.
फिर वही आएगा ना 4/3 GH under root.
नहीं अब इसमें GH कैसे आएगा? You just have to
3/4
Just have to-
3/4
square आ रहा है।
mv square.
3/4 mv squared. ठीक है. Now this velocity is in time. Okay, so this is the kinetic energy at any time t. Of course, at time t0, this would be 0. And at a later time, it would have increased. So it is, let's say it is some value of kinetic energy at time t. What would be the kinetic energy at time t plus delta t? 3/4 m v plus delta v. It's accelerating, right? It's accelerating. That means its velocity would have changed by a small amount after a small amount of time. So if this was the kinetic energy at time t, this would be the kinetic energy at delta t later. Okay. Now, what is the change in kinetic energy between these two instances? K, let's call it K initial and K final. Subtract these two and find the change in kinetic energy. Delta K, and that would be 3/4 m v plus delta v squared minus 3/4 mv squared, right? Now we expand this square, and this is mv squared plus 3/4 m delta v squared plus 3/4 m v delta v, right? Minus 3/4 mv squared, right?
Sir, shouldn't it be 3/2 mv delta v?
यहाँ पे होगा 3/2. Yes, very good. ठीक है, right? Now this cancels with this, and we are only left with two terms. All right. And now here we're going to make an approximation, because this delta t is very, very small. What that means is delta v is very, very small, no? Right? If you take the square of a small number, it becomes
So और भी
large.
छोटा हो
और
जाएगा.
smaller हो जाएगा.
It becomes even smaller. Okay, so we ignore this term. Okay, and all we are left with for change in kinetic energy is 3/2 mv delta v. ठीक है. Three by two mv delta v, and now the same. No, not yet. Okay, but this change in energy, the small change in energy must be equal to a small change in potential energy, right? And what would be the small change in potential energy? Wouldn't it be mg delta y, the change in the position, how much it has come straight down? But see, this is the picture, okay? The change in potential energy would be equal to change in delta y. Okay. What would be the delta y, this distance along the surface?
So ये हो जाएगा डेल्टा y sin थीटा.
Delta y sin theta. But we have a coordinate system. So let's say that this is delta s, then delta y would be, if the coordinate system is, this is x-axis, because that is what we have chosen the coordinate system in this case. So delta y would be delta s
Delta S sin theta.
delta s sin theta, yes. Okay. Now let's take these two energies to be equal. So we have mg sin theta delta s equals 3/2 mv delta v. Divide everything with delta t, and now do the trick that we usually do. Okay, take limit delta t to be 0. So if you take limit on both sides delta t to be 0, what does this become? Before I do that, let's cancel masses on both sides. So what do we get? G sin theta. What is delta s over delta t?
V.
V. And 3/2 and v, and what is dv by dt? Delta v by dt, delta v by delta t? Acceleration. Okay. And now the v cancels on both sides. Okay. What is the acceleration now?
2/3 g sin theta.
2/3 g sin theta. The same answer as using directly the Newton's second law. Here we have used energy method and we still get the same acceleration, right? Now, if there is no question, we have something very interesting and last bit in this lecture. So I would start with that. But if you have any questions about these things, ask now. All right. Nobody objected, but there is a problem with this energy approach. Remember, what I was doing is I was equating the potential energy, the change in total potential energy equal to the change in kinetic energy. I did not account for the energy lost due to the friction. There is friction acting on this object, right? And despite we get the correct answer. So what is wrong with what did we do? We did not do any trick. So how do you reconcile these two problems? So we have friction in this case, and there must be some energy gone into friction, lost.
सर लेकिन आप जब ये क्वेश्चन कर रहे थे आपने कहा था कि हम ये कंसिडर करें कि all the potential energies being turned into kinetic energy. आपने मतलब उसमें जब ये
Yes,
बोला
that
तो
assumption
you
is problematic.
neglected.
Yes, that's what I'm saying. So I made a wrong assumption, and I got the answer, the same answer we did get when we were using Newton's law, and there we explicitly included friction. So here I did not. Exactly, that's the point.
Sir, is it because friction is responsible for the rolling?
Yes, Yes, more or less, yes. But let's do that concretely, okay? Okay, so let's use the work energy theorem. Okay. Go from point A to B, and you have force acting, an external force, the R along the path, and then you have half m VB squared minus half m VA squared. Right? That's work energy theorem. So what are the forces acting on the, what is F in this case? Anyone?
Frictional
External
force.
force.
Sorry? Sorry, no. So
Frictional force.
yeah, so frictional force and also the weight, the component of weight acting along the surface, right? So the force is simply mg sin theta minus f. No, यही force है ना? And let's say that the length of the inclined plane is s. Okay, that would be the left side of this equation. What is the right side of this equation? Half mv square. Let's say that initial velocity was 0, so this would be the total change in translational kinetic energy. And let's say that initially it was not rotating, so the kinetic energy would be just this half m I omega square, because we are assuming that both the rotational initial kinetic energy and the translational initial kinetic energy are 0. So the change is all the kinetic energy obtained by the object, acquired by the object, right? And on the left side, we have force times the total distance. ठीक है?
सर रोटेशनल में वो m कैसे आया? हाफ i ओमेगा स्क्वायर नहीं होना चाहिए?
सॉरी, ठीक है, अब ठीक है?
यस सर.
Okay. Oh no, sorry, this is incorrect. So we are assuming that there is just the total kinetic energy, okay? So only the kinetic energy, no rotations, okay? Because we have taken into account the friction, just this. It's no, sorry, wait. No, we have this, sorry. That's a different equation. Half I omega square now we know that if we rewrite this mg s sine theta minus fs equals half mv squared plus half I omega squared, right? ठीक है. What is this s sine theta?
Height, a change in height.
Yes, mgh.
Yes, right.
All right. And what is fs?
Work done by
friction.
Work done by friction.
Work done by friction. Okay, the only problem is that it is not the same as, so I made a mistake here. So because work done by friction by moving a point on the surface of the cylinder. So this, so you have to forgive me for that. So this should be S prime, right? This is inconsistency. So it is still that you write the force, but dr in both cases is different. In this case, it is S, and in this case, it is S prime. This S is the total length of the inclined plane, and this S prime is, you see the friction is acting here, okay? And the this point, let's say, has moved by a distance S prime on the surface. So, and it makes an angle, let's say theta on the center, and we know that radius is R, okay? This is S prime. And what is S prime equal to? What is S prime equal to?
R d theta.
R theta, right? I mean, we just took theta, not d theta. So then, sorry, there is problem with my notes to look up. So, ah, sorry about that. This was the problem, sorry. So we have a work energy theorem for the rotational part of the motion, and we have work energy theorem for the translational part of the motion. Okay, we'll combine them both to get a final answer. So now this side here is simply the force is, as we said before, the force is simply mgh. If you see this, the force is actually mg's s sine theta minus fs, and the change in kinetic energy is only half m v square. Okay, and on this side, what you have is the torque, which we just calculated, f r theta, and is equal to only half I omega square. Okay, f r theta. So this is the work done and is equal to change in rotational kinetic energy, work done by the torque due to the force of friction. And this is work done by the resultant force after subtracting the friction, okay, on the center of mass. And that is equal to the change in kinetic energy of the center of mass. Okay. Now we add these two equations, left side with left side, that would be total work done, and right side with right side, that would be the total kinetic energy obtained, both rotational and translational. So, and this is H, right? So I can simplify it.
Sir,
mg.
both S are still different, right? One is S prime and the other is S.
Yes, sorry, both S are still different. Okay, mgh minus fs plus fr theta equals half mv square plus half I omega square. Okay, and now we use that analogy that we were using. So if friction moves a point by distance s prime, which makes an angle theta at the center, and this is r, then what is s prime? S prime is
R theta.
r theta. Okay, so then we can write this equation mgh minus f r theta plus f r theta equals all this. So see here, they both cancel. And what do we get?
The same equation we had.
Same equation as before. So the conservation of energy that we were assuming was not incorrect. mgh is equal to half mv square plus half iota omega square. What is happening then? What is
So
happening is, see
basically,
this. Yes, go ahead, please.
मैंने आपसे पूछना था, कंफर्म करना था कि इसके अंदर हमें ये चीज नहीं पता चल रही कि जितनी वो ट्रांसलेशनल मतलब मूवमेंट के अंदर डिस्टेंस कवर कर रहा है ड्यू टू फ्रिक्शन, उतना ही वो डिस्टेंस रोटेशनल के अंदर भी कवर कर रहा है.
Yes,
ऑब्वियसली व्हेन इट मूव्स डाउन, वो अगर आगे की तरफ जा रहे तो वो जो सिलेंडर इट आल्सो मूव्स द सेम डिस्टेंस, वो कहीं और तो नहीं होगा.
Yes, but you could look at it another way. Okay, let's say that this is the energy being dissipated. ठीक है ना, ये देखे ना, ये this equation is for translational motion. Okay, and this is essentially, you have units of energy, right? And this is the amount of energy being lost due to the friction, because friction is opposing this motion. So this much energy is being lost from the translational motion, it's slowing down. And if it was a block, okay, and there was no rotation, then we would have loss of energy equal to Fs, right? Okay. But you see this, the same force on the rotational part here, ये जो rotational equation हमने लिखी है, देखे ना, is causing this torque. Okay, so the energy that friction is drawing from the kind of linear part, the translational part, is injecting back into the system as a rotational energy. So it's drawing the linear translational kinetic energy from the system, is dissipating it, is taking it, and then giving it back to the system in form of the rotational motion. So friction plays a very important role, but doesn't dissipate any energy in case of rolling.
Right.
Any questions about this?